In the last section, we were talking about relating moles of reactants to moles of product through the use of the stoichiometric coefficients. So we were able to take those coefficients and say those represented moles of either reactant or product, and then relate those in a balanced equation and in a dimensional analysis problem. So here we're going to go one step further. And that one step is then taking that number of moles and converting that to mass. And we know we can do this through molar masses of compounds. So the aim for section 9.3 is to learn to relate masses of reactants and products in a chemical reaction. So we can see we have the equation, the balanced equation, written out above. And the problem says, suppose we have 35 grams of aluminum. What mass of iodine should be weighed out to react exactly with this amount? And remember, this term react exactly is just referring to the stoichiometric ratio, or in other words, use the coefficients to be able to convert between one compound and another. So we are looking for the mass of iodine in this problem, and we're starting with 35 grams of aluminum. So 35.0 grams of aluminum, and we have to figure out how to convert this to iodine in some way. We know we can convert from one compound to another through moles. So as long as we're in moles of aluminum, for example, we can use those coefficients to then convert to moles of iodine, because those coefficients act as a molar bridge. We can get from one to another as long as we're in moles. We can see, though, that we are starting in grams of aluminum. So our first step is going to be converting from grams to moles of aluminum. So we're going to draw our line. We're going to put grams of aluminum on the bottom and then moles of aluminum on the top. So notice this term is grams per mole. We know grams per mole is molar mass, and we can find the molar mass of aluminum from the periodic table. So locate aluminum. You'll see that the molar mass is 26.98 grams per mole. So remember that 1 goes with mole, and in this case, it's on the top. We're not quite done yet. So we need to keep going until we get to mass of iodine. So we want to get all the way to grams of iodine. We're going to continue in this same dimensional analysis problem, just with a new conversion factor. So this time on the bottom, we have moles of aluminum. Now that we're in moles of aluminum, we can convert to moles of iodine through the coefficients. So we see that they're in a balanced equation together. So we're going to put 2 in front of aluminum right here. And then we're going to put a 3 in front of iodine. So that's what allows us to convert from moles of one compound to moles of another. We're not quite done yet because we need to get all the way to mass of iodine. So we've got one more dimensional analysis step. We're going to draw one more line. On the bottom of that line, we need to cancel out moles of iodine, so we're going to put moles of iodine on the bottom. Notice along the way that we've canceled out everything so far. Grams of aluminum have canceled, moles of aluminum have canceled, and now we're canceling moles of iodine. So from here, we can go to mass of iodine based on the molar mass from the periodic table. Notice here, though, we have I2. So we have to take that mass of iodine from the periodic table and we have to multiply it by 2. And that gives us 253.8 grams per mole. You can see now we've reached grams of iodine, so we can stop converting because we've reached the unit, the desired unit for our answer. When we put this in the calculator, we're going to take 35 times 3 times 253.8. I'm just going to multiply straight across the top. And now I'm going to divide every time I see something on the bottom. So I'm going to divide by 26.98 and then divide by 2. And remember, this format just means you don't have to use any parentheses in your answer. You can still do this using parentheses if you're comfortable doing that, but it's not necessary if you just divided each step when you see something on the bottom. This gives us 494 grams of iodine. So notice what we did before was just converted moles to moles. So here we took an extra step to convert from grams of aluminum to moles of aluminum first. And then at the end, we took moles of iodine and converted from grams to iodine. This is a very similar problem, Here we're just asked the mass of oxygen that's required to react with a specific mass of propane. So remember this term react exactly? That just means use the coefficients. And as long as we use the coefficients, we're determining how much reacts exactly. Take a minute, try this problem, pause your video, and then come back and we'll go over the answer. We are going to start with 91.6 grams of propane. We're going to use now the mass of propane to convert between grams of propane and moles of propane. This is a little bit more complicated than just looking at the periodic table because we need to add up the mass of this whole compound rather than one individual element. That mass is 44.11 grams. So let's take a real quick look at how we calculated that. We know carbon is 12.01 grams per mole, and there are 3. So this gives us a total of 36.03. And then for hydrogen, we know we have a mass of 1.01, but in this compound there are 8, which means 8.08. So we add this up and we get a total of 44.11. So that's this number right here. That is the number of grams per 1 mole of this compound. That's what we get when we calculate molar mass. Now, since we're in moles of propane, we can convert from moles of propane to moles of oxygen. And we can do this because they are in the same balanced equation. So we know the conversion factor, we know the ratio, and that's 1 mole of propane to 5 moles of O2. And that becomes our conversion factor. Now that we're in 5 moles of O2, we can convert from moles of O2 to grams of O2. Remember, we were asked to calculate the mass of oxygen. So here, we're going to do a similar step that we did in the last problem. We're just calculating the molar mass of O2. Remember, oxygen is diatomic, so when it's by itself, it always shows up as 2, which means we can't just take the mass of one oxygen atom, which would be 16. We have to multiply that by 2 in a diatomic compound, which means for every 1 mole, we have 32 grams of O2. So when we put this math into our calculator, we're entering 96.1 times 5 times 32 and dividing that by 44.11. And when we do that, we get 349 grams of O2. In this section, our first aim is to learn to recognize the limiting reactant in a reaction. So this is an important concept in chemistry because it allows us to determine exactly how much is formed. So we've talked about this before, being able to predict the amount of product formed in a reaction, but it's not always as straightforward as just taking a single amount and figuring out how much is produced. It's more common that you will be given multiple reactant amounts, and you will have to determine from there how much is going to be formed. They are not always going to react exactly. So sometimes you will have more of one reactant than you will of another, and it will be your job to figure out which one is actually going to limit the amount of product that's formed. So again, the first aim is to learn to recognize the limiting reactant. We need to be able to figure out how to tell which reactant is limiting, and then to use the limiting reactant to do stoichiometric calculations. We've technically already done that. We've already been able to use a reactant to determine how much product is formed. You have to be able to just figure out which one is limiting. So when we talk about this idea of limiting reactant, we use the example of s'mores. So if you ever made s'mores before, you're probably a little bit familiar with the recipe. We're trying to figure out how many s'mores we can make if we have 2 graham cracker halves, 6 chocolate squares, and 1 marshmallow. So we're calling this the recipe for making 1 s'mores. So when we add a little heat to this recipe, you can see we get the finished product right here. So this is our recipe: 2 graham cracker halves, 6 mini chocolate squares, and then 1 marshmallow. Makes 1 s'mores. Now, if we have 6 graham cracker halves, 18 chocolate squares, and 3 marshmallows, how many s'mores can we make? So we go through the same process of adding heat to complete the recipe. So we can see that this will give us 1 s'more. This will give us 2, and this will give us 3. So we can make a total of 3 s'mores. In each of these cases, everything has reacted exactly. Now, if we have 20 graham cracker halves, 60 chocolate squares, and 1 marshmallow, how many s'mores can we make? So we don't even have to count these to determine how many we can make because we know that we only have 1 marshmallow. The marshmallow is what limits the amount of s'mores that we can make because we only have 1 of them. And that means regardless of how many graham cracker halves or how many chocolate squares we have, we can still only make 1 s'more. Therefore, the 1 marshmallow is now our limiting reactant because it is limiting how many s'mores we can make. Now, we can also say that our other reactants are in excess because we will have more of them than we need to make just the 1 s'mores that we're going to end up with. We can also think of this like hot dogs and hot dog buns and how many total hot dogs can we make. So we can see here that we've got 5 hot dogs and we've got 4 buns. So how many total hot dogs can we make? We can only make 4. That means the buns are our limiting reactant. And the hot dogs are in excess. So we can make 4 complete hot dogs with 1 dog left in excess. So the limiting reactant is the reactant that runs out first in a reaction. So we saw in this case that we only had 4 buns, so we could only make 4 total hot dogs. It produces the least amount of product. If I'm going off the dogs, I could create 5 hot dogs. If I'm going off the buns, I can only create 4. So therefore, the buns are the limiting reactant and the dogs are in excess. Now, how do we translate this idea to a balanced equation and the reactant and product possibilities? So in this equation, or this reaction, says we have 25 kilograms of nitrogen gas and 5 kilograms of hydrogen gas, and they're mixed and reacted to form ammonia. So the first thing we're going to want to do is write our balanced equation, making sure that it's balanced, because remember, if my equation is not balanced, I'm not going to get the appropriate ratio to use in my conversion factor. So here what we have to do is convert to figure out now how much ammonia is produced. So the question is asking me to calculate the mass of ammonia produced. So I'm going to go all the way to grams of ammonia. However, normally we would start with one given piece of information, but we can see here we have 2 given pieces of information. We want to figure out which reactant runs out first, but we need to do it in terms of moles and not mass. So a lot of people will just look at this and say, well, 5 kilograms is less than 25 kilograms, but remember, we cannot relate compounds to each other on the basis of mass. We can only do it on the basis of moles because we know stoichiometrically that the ratio is in terms of moles and not mass, or in other words, the coefficients are in terms of moles and not mass. Sometimes it does work out, but not always. So we have to be aware that it's a molar relationship, not a mass relationship. So what process is this going to go through? We're going to start with a certain mass, given mass of one of the compounds. In this case, 25 kilograms of nitrogen. So this is a good exercise for going through this process to be able to convert from mass to moles, moles to moles, moles to mass, and that's exactly what we're going to do. Starting with 25 kilograms of nitrogen, we know that we need to convert from one compound to another, and we know we have to be in moles to be able to do that. We're not in moles yet, we're still in mass, and we're even one step out from mass, we're in kilograms. We then have to convert to grams, then to moles. So kilograms to grams, we know there are 1,000 grams in 1 kilogram. We know going from grams to moles, we're going to use the molar mass from the periodic table. And there are 28.02 grams of nitrogen per mole of nitrogen. Now that we're in moles of nitrogen, we need to be able to use the stoichiometric coefficients, or in other words, the 1 to 2 ratio given by the balanced equation, to be able to convert from 1 mole of nitrogen to 2 moles of ammonia. Now that we're in moles of ammonia, we're going to be converting from moles of ammonia to grams of ammonia, given the mass from the periodic table. So we know if we were to add up all of those molar masses, we would get a value of 17.03 or 0.04, depending on which table you're using, grams per mole. Now I kind of glazed over this because this is exactly the same math that we did in the last section. This is review from what we did before. We're just going through this twice because we have two reactants given to us. So this comes out to 30,389. You may get a slightly different number again, depending on the periodic table that you're using, because sometimes these decimals can go out just a little bit further. So this is only half of it. We still need to take the other reactant to determine how much product is going to be formed from that reactant. And the other reactant is 5 kilograms of hydrogen. So again, we have to convert from kilograms to grams, grams to moles, and then once we're in moles, we can use the stoichiometric coefficients. So we're going to use the same process we did above because metric conversions are going to be the same, 1,000 grams to 1 kilogram. And then we're going to go from grams of hydrogen to moles of hydrogen, and that's 2.02 grams per mole because we know hydrogen is diatomic. Now that we're in moles of hydrogen, we can go from moles of hydrogen to moles of ammonia. So we can see that that's 3 moles of hydrogen to 2 moles of ammonia. And where did those numbers come from? They came from the coefficients in the balanced equation. We have one more final step to go through, and that's the same step that we used above. So we can go from moles of ammonia to grams of ammonia using, again, that number 17.03. We can stop at moles if we want to, because that will give us the same comparison value. Notice this step is exactly the same as this step, so it's almost not necessary to do it. However, the whole point of this is to determine the mass formed. So we do want to go the entire way. If we were just asked which one is the limiting reactant, we can just compare those on the basis of moles. But if we're asked to determine the mass formed, we want to go all the way to mass at the end. So after doing this math, we can see that from hydrogen, we have 28,102 grams of ammonia formed. Now, we have two masses that are formed, but only one of them is correct. So remember when we were looking at our hot dog example, we were only able to take the answer that produced the smallest amount. So that's what we were looking at here as well. So this is going to be our answer, 28,102 grams of ammonia. And that's because I cannot produce any more product than the limiting reactant will allow me to produce. In other words, the smaller answer is the correct one. Now we have to make sure we're answering all of the questions. So the question here is to calculate the mass of ammonia produced, which we did by saying it was 28,102 grams. However, if you are asked to identify the limiting reactant, reactants only exist on the left side of the equation. So it's going to be one of those two. Whichever one produces the least amount of product is your limiting reactant. So therefore, hydrogen is going to be my limiting reactant. Just make sure that you are answering both questions if they're both there. How much is produced, and identify the limiting reactant. So the amount produced is 28,102 grams of ammonia. The limiting reactant in this specific case is hydrogen.